YouTube channel. So today and for now, I'm going to explain to you the molecular orbital theory part 2, where we will discuss about the molecular orbital configuration. So what are the theory for the molecular orbital configurations? First one is, this is similar to the hybridization, where the number of molecular orbitals, or we call it as MO, form is always equal to the number of atomic orbitals combined. Second one, the more stable the bonding molecular orbital, the less stable the corresponding anti-bonding MO. And the third one is, the filling of MOs proceeds from low to high energy, from the bottom to the top. And for the fourth one, each molecular orbital can accommodate up to 2 electrons. And number 5, use Hund's rule when adding electrons to MOs of the same energy. And last one, the number of electrons in the MOs is equal to the sum of the electrons on the bonding atoms. So for the second one, we follow, for the second theory here, we follow the Aufbau rule. While for the fourth one, this one we follow the Pauli exclusion principle. And yeah, this is the energy and also shape of hydrogen in molecular orbitals. So what happened here? We have two isolated hydrogen atoms, where each of these hydrogen atoms has one proton number, or one electron for each here. This is where we have the 1s1, and another one is also 1s1. So in order to form the molecular orbitals for the hydrogen here, we need to add one hydrogen here and also one hydrogen here. And also second one, we need to subtract in order to form the anti-bonding. So for the first one, here we have a potential energy. Alright, this is the energy. Alright, and then let's say we add on these two isolated hydrogen atoms, it will form a bonding MO. Alright, so this is the this is the Lewis structure of the hydrogen, where each of these hydrogen share one electron. So what happened here? A single bond here will form a sigma bond. So what we have here, we have a bonding MO where we have the sigma 1s. It based on the atomic orbital of the hydrogen atoms. This one is the first one when we add. A second one, when we subtract each of these isolated hydrogen atoms, what happened here? It will form anti-bonding MO. Alright, so in this hydrogen, we only have the sigma level. So we have the sigma and also pi. Right? So because we are dealing with the 1s orbitals, so what happened here? Alright, it will form a sigma star 1s. Sigma star 1s. While for this one is sigma 1s. So for the anti-bonding, we have a node here, where all the electrons are moved further away from the node. So node, this is where we have zero probability to find electrons. So this is what you need to have in order for you to draw the molecular orbitals. So you need to show the bonding and also anti-bonding, right? So the bonding molecular orbital is always lower in energy, while for the anti-bonding here, is always higher in energy compared to the atomic orbitals that combine to form them. Why the bonding molecular orbital is lower in energy? Okay, this is the differences between the sigma star anti-bonding MO and also sigma bonding MO. First one, alright, if you look at back to the previous slide, okay, for the sigma star anti-bonding, it has node between the nuclei, okay, and then the electron density is outside the internuclear region, and this is what happened, okay, the electrons do not shield the nucleus, so it increases what we call increases of nucleus to repulsion. So when this increase, okay, the repulsion increase, so what happened here, the antibody will have higher energy. And for the sigma star antibonding or pi star antibonding, the molecules less stable when it's empty. Okay, then let's look at the sigma bonding MO, where the atom spread between the nuclei, and then the nuclei attracted to the intervening electrons, and electrons being delocalized its charge. And another one, electron repulsion reducing make MO lower energy. Okay, and molecules are more stable than separate atoms. Okay, so for the molecular orbital configuration here, okay, the order of molecular orbital configuration start from the sigma star, and then followed by pi and also pi star. Usually if we have pi and pi star, we will be dealing with the p orbital. Okay, while for the sigma and sigma star, usually the atomic orbitals, we will be dealing with the s or orbital. Okay, alright, so okay, how to write the molecular orbital configuration? Okay, so for the hydrogen here, okay, so we have the molecular orbital of hydrogen here. This is the sigma 1s. Right, let's say we have the hydrogen first. Sorry, this one is where we have the anti-bonding. Alright, so this is the sigma star 1s. How to draw the molecular orbital configuration? How to write the molecular orbital configuration? Okay, so for the hydrogen, we start from the bottom to the top. Okay, so we have the sigma 1s. So sigma 1s in bracket, how many electrons do we have here? Alright, so this is 1s1, this is 1s2, so 1 plus 1, we will have 2 here, and then followed by sigma star 1s. Okay, how many electrons do we have here? Okay, we only have 2 electrons, and then this is already occupied 2 electrons, so this is become 0. Okay, alright, so this is the sequence that you need to follow in order to write down the molecular orbital configuration. Sigma, and then followed by sigma star, pi, and also pi star. And alright, okay, so that's how we write down the molecular orbital configuration. So that's all for part 2. I will see you guys in part 3. Bye.